I'm filming this preface after I finished shooting the video, and the video got quite long. So if you're just interested in the results, how to fix certain problems on your one-wire bus in conjunction with a DS18B20 temperature sensor or other one-wire devices, use the index in the description and jump to the wrap-up. There you find a summary. Anyway, it will take me the better part of half an hour to get to this point. I did it! I did it! No more glitches! And right before that, I was at a very bad place. Even after I managed to find a principled solution to my main problem, it took me another, not quite the better part of a half hour to perfect it so that my controller worked really perfectly. I thought about, cutting the video together, but I think you can learn a lot from my mistakes and learn a lot about, chasing flukes that only appear now and then. So enjoy. That's where we left off last time, with the working hardware of the controller for the laboratory water bath. Well, almost working, because we observed now and then some glitches in the temperature readings of the sensors within the water bath. And of course, no glitches now. Yeah, typical. Ah, there, you saw it? Okay, so that's the problem with glitches. They are just glitches. And again. And we know several things about them. First, as I said, they only happen with the sensors in the water bath. So the sensors that go through the digital isolator. The external sensor that is not isolated shows no such problems. And the other thing we know about these glitches is, let me switch off mains AC and power the whole thing through USB. The glitches do not appear when the whole thing is powered via USB. See, a whole minute went by, not a single glitch while powering the whole thing from a USB power bank. So, let's take a step back and analyze what's going on here, because I really don't like to handle these glitches in software. I also don't like to debounce my rotary encoder in software, and these glitches would be much harder to handle. Let's have first a look at the one-wire signal of the working temperature sensor, the external one that is connected via the 3.5mm jack here. While I was cutting the video, I noticed that it's not always perfectly clear where I connect my oscilloscope probes. So I created these little inserts afterwards to show you exactly that. To the left, behind that green line, is my controller with the Arduino, and the Arduino has two outgoing one-wire buses, each with a pull-up resistor, and they go through a digital isolator, and then they have two more pull-up resistors for the isolated side and go into a big connector. The big connector also carries the AC mains for the heater of the water bath. And this goes all through a thick AC power cable to my water bath. Here to the right, behind the black line, where two DS18B20 temperature sensors are connected. And AC mains obviously goes and ground to the heating element and the metal parts. The Arduino also supports a third one-wire bus, which is own pull-up resistor, and that is directly connected via a 3.5mm jack and 1 meter of signal cable directly to a DS18B20. That DS18B20 is working perfectly fine, and I'm probing right here at the pull-up resistor with my oscilloscope probe. So I did a single shot here of the signal, and yeah, I also used a cursor so we have a reference when you look at the other signals. But yeah, high level is aboutish 4.7 volts, low level is, yeah, 0 volts. And if you look at the waveforms, and I can scroll through that signal, they look squarish enough for my taste. I'm probing now here at that pull-up resistor at one of the affected one-wire channels directly after the Arduino. Now, that's the signal going from the Arduino to the digital isolator, or between the Arduino and the digital isolator. The voltage levels are the same. Yeah, you see here we are not going quite down to 0 volts. Why that is with the digital isolator, I explained in a video, card link. And yeah, the rest of the signal looks just peachy. My probe is now connected here at the pull-up resistor behind the digital isolator. Now we're looking behind the digital isolator. So yeah, the first thing we notice is that noisy stuff here. That's a little bit, how you doing? But let's first zoom in into the signal. Yeah, the signal looks good enough. Yeah, the rising edges are not as sharp, but it's within, yeah, what you can tolerate. But if you zoom in here later on, you see these rising edges, they really look bad. And that's the first indication for what might go on here, and that is that our pull-up resistors on the one-wire bus are maybe a little bit too small. But that's only one point. The other point was that we have this noisy stuff here. And that's something I would expect if the sensors would be running on parasitic power, which they shouldn't. So yeah, maybe we have two problems here. One with the wiring and second one with the pull-up resistors. I'm measuring again at that pull-up resistor here. But so far everything was working from the USB power supply. Now I switched over to mains AC power. And we see here that's the signal again from the good sensor, yeah, without digital isolation. We have a little bit different voltage levels. Let me zoom in here just a wee bit. And a little bit more noise, because yeah, now we're not running from lithium ion, but from a switching power supply under quite a load. But yeah, otherwise a little bit different voltage levels. The signal itself, the edges, yeah, there you can see the switching noise. It's really annoying. Yeah, they are as sharp as ever. And in addition, on the good sensor, we also don't have that noisy stuff here, these real hard spikes. Okay, let's probe the output from the Arduino to the digital isolator. So we are probing at that pull-up resistor again. Yeah, at that scale you see a little of that noise here right after our data package, but the data package itself, yeah, this here is an artifact from the digital isolator. Looks good. I mean, we have the switch mode power supply noise here, which is not that fine, that nice, but it is what it is. But otherwise, yeah, that looks good. Moving the probe to the pull-up resistor on the isolated side. And at the other side of the digital isolator, we still have in the signal these very slow rising edges, probably caused by pull-up resistors being too small. And if I change the scale and we go to this portion of the signal here, we have that noise. Again, that indicates that the sensors are working on parasite power. And my circuit is not designed to provide parasite power. So, first order of today would be to check the connections from the board through, yeah, the long, thick cable to the sensors in the water bath. Yeah, and probably the long, big cable is the reason why my standard 4.7K pull-up resistors are too small and we have these really smooth, slow rising edges in the signal. Nope, at first glance it looks that I got 5 volts coming out here between my 1-wire ground and 1-wire 5-volt line. Let's check the resistance. 0.2 ohms, so basically nothing for the 5-volt line. And 0.4 ohms for the ground connection. So, well, 0.3. So that seems to be okay. The only thing I can think of is that somehow a wire is broken here. But I mean, these are hookup wires. They might break. But the connection, 5-volt connection, broken to both sensors? I don't think so. Or both sensors may be damaged from the very first test. Yeah, card link that failed. It got quite warm in here, but no, I don't think so. Especially the sensor back here, which gives us more frequent bad readings. No, can't be. So let's get back to our 2 pull-up resistors down here and make them smaller. So if it's not the 5-volt connection or the ground connection to my DS18B20 sensors in the water bath, it must be the pull-up resistors. And I replaced those now, yeah, they were 4.7K with 1.5K. Within tolerances, yeah, expecting a maximum supply voltage of 5.5 volt, yeah, plus minus 5%. The resistors, that's as small as I can go with the DS18B20s, because they only have a guaranteed minimum sync current of 4 milliamps, okay? If you try to sync more through them, they won't be able to pull down the signal line really to 0. Measuring again here at that pull-up resistor. And if we have a look at the scope, yeah, measuring the isolated side of the one wire bus and power supply is from a USB bank. Yeah, that's one of the very short pulses, and it's a difference like day and night. I mean, you still have here yeah, a not very sharp rising edge, but yeah, if you put that into perspective, that's completely okay. And as I said, that is one of the very short pulses. So no problem there. We still have this scruffy stuff back here. I have no idea where this is coming from. As I said, usually I would expect to see something like this if they run off parasite power. Yeah, the DS18B20s, that is. Yeah, no idea. Let's probe the other channel if it's also looking good, and then switch over to mains AC power and see if we experience any more glitches. And now at the pull-up resistor of the other one-wire channel. The other isolated channel is looking good too, and yeah, as I said, or as I did before, I'm looking at one of the very short spikes here. And, well, we have the grizzle here. That's when the DS18B20 does its temperature conversion. And as I said, normally you see that when you run them on parasitic power, not on direct power. Let's do the same with AC mains power. I stayed with my probe at that pull-up resistor here. AC mains power looks also good. And if I look at some really small peaks here, yeah, that group here in the middle. Yeah, a little bit more noisy, but still more than good enough. And of course, there's still that stuff here in the back, and I have no idea why. Unfortunately, there it was. We still have these glitches, but as far as I can see, only on that sensor. Yeah. Never saw a glitch on that one after we changed it. And here we have it. Again and again and again. And I have to say I'm a little bit weary now. Let me try something first. Let's switch off the heater and let me get a stopwatch. Okay, my theory is, because I saw that before, when I didn't give the DS18B20s enough time for their temperature conversion, then you get nonsense values out of the things. And yeah, I'm using here a nano every, which is running at 20 megahertz, and all other nanos are running at 16 megahertz. So maybe there is still a bug in the software environment, and yeah, the delay function I'm using, yeah, between each time I poll the temperature sensors is buggy. Let's see, I'm counting now. So I counted twice, and both I came to 73 cycles per minute. So I counted not 73 cycles, but 73 offs. An off is only displayed every second cycle. So one cycle took 60 seconds, divided by 73, divided by 2, 411 milliseconds. And within a cycle, or yeah, an Arduino code, the loop, I first read the temperatures from the sensors, then I do some stuff like updating the displays, then I request a new temperature conversion for the sensors, then I have a delay statement of 375 milliseconds, and then yeah, I start again in the loop with reading the temperatures after 375 milliseconds. And yeah, the delay for the 4 megahertz faster Arduino every seems to be okay. I mean, 33 milliseconds for all the updating stuff yeah, that's realistic. So there is a delay of 375 milliseconds. Anyway, I slowed down things by a factor of 2, and I'm still getting glitches. Of course, now I don't get a glitch. There it is. So yeah, it's not a timing problem regarding the temperature conversion time these big glitch DS18B20s need. It's also the signal looks now good. So I'm wondering if I might have actually, yeah, in that fateful first test that failed, fried the sensors. Maybe, yeah, they got overheated. I mean, temperatures went up to 150 degrees. Yeah, measured with thermocouples. So next step, replacing the sensors. I'm getting kind of desperate. I desoldered one sensor in the water bath and connected there. Yeah, that's that nest. Two oscilloscope probes, one measuring the signal line, one measuring the power line. And yeah, the power line is displaying 5.18 volt perfectly. I'm also measuring the data line of the second isolated channel. And this is all available on the scope. And so I'm probing the isolated 5 volts and one wire channel directly here at an DS18B20 sensor, and the second one-wire channel here at the pull-up resistor right after the digital isolator. We will have a detailed look here, and there are some surprises. So that's the signal at the end of the line from the master, or what comes out of the digital isolator. Now, when we zoom in here, zoom out a little bit, you see there's still spiky stuff, and yeah, this has to come from the digital isolator or the master. One would assume, right? Now let's activate the second data channel. You see what? It's not something that's going on my first channel, but these spikes are caused by the activity, yeah, before on the other channel. Yeah, if we look at the power rail in that time frame, I mean, this is over 2 volts noise on the power rail. Yeah, check your powers. So something is definitely wrong here. Well, a look into the data sheet for my 100 milliwatt DC-DC isolated converters informs me here right away, first line, short circuit protection, short term 1 second. Yeah, when I had the digital isolator the wrong way around, the power rail went down to 0.5 volts. So yeah, basically a short. And I did that for minutes at a time, yeah, several times. So might be time to get the board out again and put a new one in. Still probing the 5 volt and the signal directly here at the DS18B20 sensor. Nope, replaced that DC-DC converter, and yeah, we have still spikes, and if you look into them a little bit finer, they are about, yeah, it's a ringing. It's really these cheap DC-DC converters. If you suddenly pull, yeah, 4 milliamps or so, or a little bit less than 4 milliamps through the pull-up resistors, that's the reaction. I mean, come on! Over a volt up, and over a volt down again, and then a little bit ringing until... and of course, that is reflected, that's what we saw, that is reflected in the data line. Yeah, not the spike up, but the spike down. Oh, Jesus. Haven't moved the probes, they are still here at the DS18B20. I botched in a 0.1 microfarad ceramic capacitor just where I connected the probes. I'll give you a close-up in a second. And yeah, they're gone, but they are still on the data line. So I'm not sure if that is really a power supply problem or if that is crosstalk in this pretty long big cable. And yeah, there in the distance you can spot the, can I point it to it? The tiny 0.1 micro capacitor. This is getting ridiculous. So let's take a step back and see where we came from and what we've done so far. So on the controller side, I have my DC to DC converter providing my isolated 5-volt rail for the whole shebang. I have my digital isolator, only drawn 1/2, that uses that 5-volt rail, gives us 2 bidirectional digital channels, open collector of course, and yeah, that always had a decoupling capacitor of 0.1 microfarad across its power rail. And yeah, we saw no problems here. We had initially the usual 4.7K pull-up resistors on our 1-wire buses, and then we have these 2 big connectors with 1 meter of a power line running between them, and 4 wires in that power line are used for our 5-volt rail and our 2 1-wire buses. And on the bath side, we simply had 2 DS18B20 sensors. Getting 5 volts. No phantom power, and each with its own 1-wire bus. Now, when we looked at the signals here, on that side with our oscilloscope, we saw slow rising edges. So we decreased the size of the pull-up resistors from 4.7K to 1.5K, which is, with a limit, you cannot make them much smaller than that. And that solved the problem. Our rising edges, they have still a little slope, but it looks okay, absolutely okay. Then we saw, when I took out one of the DS18B20s, and by the way, we checked, they have not been damaged in any way, as we have exchanged the DC to DC converter, which is also not damaged. Anyway, we saw these 2 volt spikes on the 5-volt rail, which is not very nice. We don't know if that was the supply. We suspected the supply, but obviously not. Or is that crosstalk between the different lines? And I botched in, or permanently botched in, now 1 microfarad capacitor here on that connector and a 1 microfarad capacitor here on that connector. And let's see if the problem is permanently solved. We already saw, if I just botch it in here, it's okay, but now I'm decoupling my big cable here, the lines on both sides. Haven't moved my probes, still attached here at the DS18B20. Now let's have a look at the results on the oscilloscope. Yeah, right away the spikes here, the crosstalk from the other channel, it's back again on my blue power rail. Yeah, I'm still measuring directly at the DS18B20. And we have also spikes here on the power rail when the DS18B20 is active itself. But the spikes here are about 700-800 millivolts. Let's zoom in on that. Yeah, that's not too bad. Yeah, maybe 600 millivolts peak to peak. That's survivable. I mean, it's not as nice as when I put the 100 nano directly to the pins of the DS18B20, but then the DS18B20 has an internal capacitor. Yeah, it doesn't feed directly from the 5-volt rail. But we still have here an undershoot, yeah, that crosstalk from the other sensor. Yeah, that's easily 1.4 volts. But it's not going too far down that it could be interpreted as a low by the DS18B20. My signal, yeah, that's a short pulse. It still looks okay. We have also here the ringing, which is, yeah, a good volt. Peak to, more 1.4 volts on the power supply. But yeah, and here that ringing, it's not nice, but it's a one-wire bus. I don't know. I've read in some papers that they actually on long wires, and we don't have a long wire, add an RC element to the data line. Let's see what happens if I put a small capacitor just on the data line. So I don't know, 1 nanofarad or something like that. But before that, let's do the same measurement in the controller on the board itself to see what's happening there. My probes are back in the controller here at the pull-up resistor and here at the power rail. So that's measured directly across the pull-up resistor. So the signal, of course, on the one side of the resistor and power supply on the other. And if we scroll, zoom in there, the power rail is in the crosstalk region, completely okay. And yeah, we still have that, and on this side it's just 1 volt on the data line crosstalk. And if I look at one of the really sharp short pulses in the signal, yeah, we still have that ringing here when we go down to low, but yeah, let me try to put in, as I mentioned before, a very small capacitor between the data line and ground, and let's see if we can get rid of that ringing here, and foremost get rid of that crosstalk. I mean, this just looks ugly. Didn't move the probes, still here at the pull-up resistor and the power rail. Now that we don't have to zoom in to see that makes things just worse if I have connected everything right. I admit I'm at a total loss here, so I decided to let the serial monitor on my notebook, connected via the USB port of course, monitor the values I'm reading on all 3 sensors, and I will do a little statistic seeing how often that error or that intermittent error occurs within about half an hour. And yeah, from there I will decide how to proceed. Attention, probes are now back at the DS18B20, signal and power. I did it! I did it! No more glitches! Well, I couldn't believe it at first, but it worked. It worked, and the solution is so obscure, and yeah, give me a sec. Anyway, I'm staring now quite a while on my display here, and I see a glitch. Well, but that was the first glitch I saw in a very, very long while. Was that really a glitch or just a trick of the eye? I don't know. Anyway, now I'm uncertain. Anyway, what I did was to add, yeah, you see that little blob there? That's a Schottky diode in reverse polarity between the signal line and the ground. And what it does is to cut off, yeah, these undershoots here when on the falling edge. You remember these undershoots were going, yeah, they were touching the -1 volt line, probably they extended below that, and that Schottky diode is now capping them off. Anyway, while I was waiting that half hour and recording the measured values via USB port, I surfed a little bit more. I mean, I Googled before a problem with glitches on one-wire bus, but then I came upon a very obscure link. And I found, a second link that linked to the first one, and both referenced a Maxim document which no longer exists. I had to go into the Wayback Machine on the internet, back to the, I don't know, 90s or something, to find that document, and it described a technique where you put a reversed bias senor diode here on the signal line of your one-wire devices to cap off these undershoots on the falling edges of the signal. And I didn't know that, but obviously these thingies are quite sensitive to such undershoots because their internal parasitic power circuits, they have some diodes in them, 2 ground and 2 5 volts, and if something between the signal line and 5 volt, and if the signal line goes below 0.7 volts, that can do funny things to them. At least that's how I understood the article. Put links, no cards, just links in the description. And they recommended Schottky diodes 1N5817. I couldn't get them here in my hometown, so I took 1N5819, which is basically the same Schottky diode but with a higher voltage rating, and that's what's currently there on my sensor on the data line and ground. But maybe some 20 years later or even longer, we can do even better, because I have here 2 other Schottky diodes. I don't know which is which. I went shopping and bought a lot of Schottky diodes, obviously. This one should have even a smaller voltage drop on small currents. And this one, or the other way around, I think this one is a high frequency one for a radio frequency application, which should be able to react even faster to these sharp spikes. And that one has comparable to the 1N5819 lower voltage drop at very, very small currents. So let's try if I can do even a little bit better. Probes are still connected directly to the DS18B20. So that's my signal with a BAT48, which should have at small currents a smaller voltage drop, but is obviously not as fast, or not fast enough, because you see the spikes, the negative spikes are longer again. And I placed the cursor at the longest spike I observed with the 1N5819. Now let's see what a radio frequency Schottky diode can do. And yes, the glitches are back. If you don't believe me, we just have to wait a second or so. Ah, there, glitch. Okay, we had to wait 5 seconds or so, but yeah, it's glitching. It's noticeably glitching. Haven't moved the probes, still here at the sensor. Nope, the BAT48 radio frequency Schottky diode does even a worse job. So you see almost all spikes are touching the -1 volt line again, and maybe are even going beyond it. So yeah, the advised, what was it? Yeah, 1N5817, and I have a 19 here. They are marketed as rectifiers for switching power supplies. So they are obviously designed to take sharp spikes, fast and sharp spikes. So I will permanently botch in some of these Schottky diodes here, reverse bias to the ground on the data lines. Yeah, I probably solder them in at the connector like I did with the 0.1 micro capacitors here for the 5 volt supply line. And then we have a measurement again, and then I will do a statistic again, let the thing run for half an hour and record the values, and then go to my Excel and see how many glitches I still have. Okay, I botched in the 2 diodes, the Schottkys here from ground to one signal line, and yeah, they're down below the other one from ground to signal line, and yeah, here's my 0.1 micro filter capacitor or decoupling capacitor on the power rail. And yeah, I didn't put my heart into it because yeah, after studying the data sheets a little bit more in detail, I learned there is a significant difference between the 1N5819 and the 1N5817, and it's not only the rated voltage, it's also the forward voltage drop, which is significantly 100 millivolts or so lower for the 1N8507. But I don't have 17s, I only have 19s now. At some point I might replace them or find a better solution. Anyway, let's connect everything up and have a look at the oscilloscope. That didn't work out so well signal-wise when I probed it with the scope, and I spare you the view at the scope accompanied by my inappropriate language. So I created some little perf boards here carrying the Schottky diode, the decoupling capacitor, and yeah, a few wires for test points for attaching the oscilloscope properly. And please also note the excess amount of thermal goo down here where the sensor is pressed to the bath. Let's see how this works. Probes are still here at the DS18B20, now hooked to my newfangled professional test point. And it works beautifully. So my spikes down here are now all limited to minus 520 millivolts. That's within specification in that very old document. Yeah, not 1990 something, but it is from 2000, or it was available until 2004 in the Wayback Machine. Yeah, and I also think, but I would have to make a comparison when I cut the video together, that the crosstalk is also a little bit lower, so maybe a 1 volt, 1.1 volts or something like that. Let's have a look at the edges of very small pulses. Yeah, there we have one. Yeah, still more than satisfying. I haven't noticed any erroneous temperatures displayed here for a while now, but just to be on the safe side, I will connect my notebook with USB and record the temperatures for half an hour, put it in Excel and see if I can find some errors in, yeah, let's say within 2,000, 3,000 measurements. And the results are in. So this numbers here, that was the 1 hour measurement I did without the Schottky diodes. So a total of 2,376 measurements. And I had 19 erroneous readings on the heater sensor, so about 0.8%. On the bath sensor, that was the upper display, where you could watch the errors appear, 133, that's a whopping 5.6%. So more than every 20th reading was wrong. And that's the numbers I did just now with the 1N5819 Schottky diodes in. Yeah, got impatient. I just waited for half an hour about it, so I got only 1,148 measurements, but only 2 erroneous readings on the heater. That's down to 0.17%. On the bath, still 28 erroneous readings. Yeah, but that's also down significantly to 2.4%. And remember, I'm using the wrong Schottky diode. The Schottky diode recommended by Maxim is the 1N5817. And the important thing here is that the 1.7 has significantly smaller forward voltages than the 1.9. Yeah, the smaller the current, the smaller that difference gets. So for 0.1 amps, it's a meager 20 millivolt. The important thing here is the 1.7 has much smaller semiconductor layers. There's also less capacity probably in the diode. And yeah, it's faster. It's still a wee bit faster than the 1.9 that is designed for, you can read it, I can't read it for 40 volts instead of 20 volts. And yeah, so I guess as soon as the 1N8517 arrive and can put them in, things will improve even more. It's a few days later and I received my 1N5817 Schottky diodes, and yeah, I soldered them in and I redone these perf boards here holding the decoupling capacitor, the Schottky diode, and my test points. Yeah, looks a little bit neater, and at the same time the leads to the temperature sensors and these back to the big connector. Can I get it in shot? Yeah, I shortened them as much as I could. So let's connect the oscilloscope and have a look at the signals now. And I'm probing again here directly at the sensor. And if we look at the signal and the undershoots, yeah, it certainly looks different, but yeah, my cursor line down here is at minus 800 millivolts. So the deepest spikes really haven't improved at all. But yeah, there are groups here which are really nicely capped at, let's get the cursor up here, at minus 440 millivolts. But if I remember right, before we had, yeah, the maximum spikes on that sensor at minus 540. And we didn't have this really, really low spikes here. So not really an improvement, but let's make a statistic. Well, the numbers are in and it's a little bit disappointing. Yeah, I have more samples this time, again 2283. I observed 2 false readings on the heater sensor. That brings us down, yeah, from 0.17% to 0.088%, but that's not really statistically significant. The same for the bath sensor. We are yeah, up in count to 54 errors in these 2000 something samples, which equates to aboutish 2.4%. And if we take more decimals here to the percentage number, we see a very slight improvement, but also not statistically significant. And yeah, we're using now the prescribed 1N5817 instead of the, yeah, similar but not absolutely equal 1N5819. There's one last thing I want to try. I mean, we changed the pull-up resistors from 4.7K to 1.5K to get our rising edges really nice. And they are, but they don't really have to be that nice on a I2C bus. The rising edges on a I2C bus, yeah, with pull-up resistors and open collector pull-downs are always a little bit so maybe when we increase the value of the pull-up resistors again, just a little, yeah, not as to 4.7K again, because that didn't work, obviously, we can limit the undershoots a little bit more. I changed the pull-up resistors here after the digital isolator from 1.5K to, yeah, I'm using Post-it now, 3K. Yeah, initially we were at 4.7K, so that's somewhere in the middle. And my probes are still connected directly here at the temperature sensor. My rising edges at very short pulses are still, yeah, okay, borderline, but acceptable. At least on the oscilloscope there is no noticeable change in the undershoots. So the only thing left for me to do is run the thing for half an hour again, and do a statistic. And we finally did it! Zilch wrong temperature readings on the heater sensor and zilch wrong temperature readings on the bath sensor. So yeah, increasing the pull-ups again to 3K solved our problem. So we went in the very beginning with our pull-up resistors from standard 4.7K to a very aggressive 1.5K. That solved some problems. And now we go back to 3K and everything is fine. And I called that, yeah, 1 was our first step going to 1.5K. I call that 1A. Yeah, we're still handling the slow rising edges, but we are not that aggressive with the pull-up, so our rising edges are good enough and everything's working. it's finally time to wrap things up. So this is all what we did that actually had some effect. And I start with the 2-volt spikes on the 5-volt rail we were observing. And yeah, that was actually crosstalk from the data lines. And we solved that by adding decoupling capacitors between ground and 5-volt line near the DS18B20, and afterwards, yeah, some noise, of course, on the 5-volt rail, but otherwise it looked fine. We do not know if that actually solved any issues, but a nice clean power rail is always a good thing. Then we observed these really slow rising edges. Yeah, it looked ugly, and that was, in hindsight, causing communication errors between the Arduino and the DS18B20. So yeah, we solved that by aggressively making the pull-up resistors smaller. So we got a really nice, here in red, a really nice signal, and that took care of communications errors. Finally, we had this crosstalk on the data lines. I forget about that for a second, but foremost, these large undershoots, which I ignored for quite a while. They went down, yeah, at least -1 volt, probably further. And these undershoots, as I learned, cause the DS18B20 to malfunction. And yeah, we suppressed these undershoots by adding reversed bias Schottky diodes from ground to the signal line, again, like the decoupling capacitors near the DS18B20. Yeah, that took care of most of the undershoots, and yeah, remember the crosstalk, also reduced the crosstalk. But we weren't there quite yet. We had to increase the values of our pull-up resistors again. Yeah, made our signal not that nice, but nice enough so we didn't have any communication errors. And that in turn also influenced, in a good way, the undershoots. Meaning the first time we put in this really aggressively small pull-up resistors, we probably made the undershoot problem worse. So yeah, we have a little feedback loop here. Let's talk about the elephant in the room. I always had that third DS18B20 temperature sensor attached, yeah, nicely installed in this glass tube, which I melted shut, yeah, card link, yeah, so I can put it into the etching solution, and it's attached to the controller by a 1 meter cable, signal cable, made to carry signals. And we never had problems with that one. The other 2 sensors in the water bath itself, which gave us so much trouble, were also connected by just 1 meter of cable to the controller. But this is AC mains cable, not designed to carry signals. And all the parasitic capacitance and inductance and, yeah, capacitive coupling between the wires and inductive coupling between the wires, it messed up our signal completely. And yeah, in the end, this cable is the reason we had to go through all the trouble here. So next time you see my controller, it will be all closed up, nice and tidy, and we can finally talk about software and temperature regulation. Till then, bye.